Okay, in the last slide, we have shown some two-dimensional potential surfaces, but in fact, there is a better way to visualize the potential change, which are equipotential surfaces. Take a look at some examples shown on the right side. There are several surfaces drawn together, and these are equipotential surfaces. And what we mean by that is if you choose one of these surfaces, and if you stay within this surface, everywhere the potential will be the same. That's what we mean by equipotential surfaces. And one important thing about equipotential surfaces is that no work is done when a charged particle moves from one place to another within an equipotential surface. So this is an example like this. So if you are moving from this position and follow the surface and then stop at this position, then there will be no work involved. It's just like you are moving on a flat surface, in a gravitational force. Okay, and then another example here. So if you are moving from this position and go out of the equipotential surface and eventually come back to the one position in the same surface, then in this case, even though the path looks more complicated, you are still starting and then ending at the same equipotential surface, so still no work will be done during this motion. Okay, and then when you are drawing equipotential surfaces, there are two important rules you have to follow. The first rule is that the surface will always be perpendicular to the electric field lines, just like this. So on the right side, these lines are actually electric field lines, and then here you see that it's electric field lines and equipotential surfaces are always perpendicular to each other. This is the first rule you have to follow. And then for the second rule, let's take a look at another figure. So remember, when you are drawing equipotential surfaces, you end up drawing many of them, right? And then here, for example, here there are 1, 2, 3, 4, 5, 6, 7, or even more equipotential surfaces. And when you draw them, remember you have to always draw them with equal intervals, which means that the difference in electric potential, say between here and here, must be equal to the difference in electric potential between here and here. Okay, it's always the same. And then see that the electric field is actually going from left to right. And so what does it mean? So which means that electric field will be, electric potential will be high on the left hand side and low on the right hand side. That is why electric field goes from left to right. Okay, and then how about the case of positive point charge? So here it looks like a spider's web, but anyway, the two rules that we have discussed are exactly followed. So electric field lines and equipotential surfaces are perpendicular to everywhere, and then you see that in the middle, these equipotential surfaces are very densely populated, while it is very coarse far away, which means that now electric potential is changing rapidly near the point charge, but it's changing more slowly far away from the point charge. Okay, and then what if you have a negative point charge in the middle? Basically they look the same, but the only difference is that now electric field is going in the case of negative point charge. So therefore what you can say is that in the case of positive point charge, electric field was higher near the charge, but in the case of negative point charge, the electric field will be higher far away from it. Okay, and then if you have two positive charges, then the equipotential surfaces will look more complicated, but whatever happens, the two rules that we have discussed between the equipotential surfaces and electric fields are all satisfied. Okay. Okay, then let's try more quantitative calculation of an electric potential for a certain case. And the example here is an electric dipole. You know, electric dipole is a pair of two equal and oppositely signed charges. So as in the figure on the right side, we have a plus Q, minus Q, which is an exact electric dipole. Okay, and then we are trying to calculate electric potential at any position around this electric dipole. And for our calculation, let's take the origin of our position to be the middle of the electric dipole. And then here you can see that then positive charge will be above the origin at the distance d/2, right? And then the negative charge will be below the origin at minus d/2. Okay. And then how do we calculate the electric potential? Well, we have more than one charge, so we are calculating electric potential independently from the two charges and then make a summation, right? So we are actually doing this. So let's call V plus to be the potential due to the positive charge and V minus to be the potential due to the negative charge. And then each of them, well, the initial expression is simple. The positive charge will have plus Q and negative charge will have minus Q. And then let's express the R plus to be the distance between the positive charge and the current position that we want to consider, and R minus to be the current the distance between the negative charge and then the current position. Okay, and then the KQ comes out, and then you can just simply try to write it this way. Okay, and then here if you take a look at the figure, then the difference between R minus and R plus may be a little bit difficult to calculate, but remember, we always take this electric dipole to be very small. So if it's small enough, you know that we can approximately say this direction of the R minus and then the direction of the R plus are almost parallel to each other. And then if they are really almost parallel to each other, then the difference can be simply calculated just like this, which is the now d multiplied by cosine theta, right? Okay, this is not equal, but approximately, because we are considering that R is very far away compared to the distance of d. Okay, and then again, if this d is much smaller than R, then you can say that R plus and R minus are in fact not very different from each other. It's almost close to each other and also to the R, so which is the distance between the midpoint and then the current position. So therefore we can again approximately say that R plus multiplied by R minus is almost similar to R squared. Okay, and then if you have got this, then you can simply insert them into the above equation, and then finally summarize that the electric potential will be KQ multiplied by d cosine theta divided by R squared. And then remember, the QD was the definition of the electric dipole moment, which is P here. So you can see that now finally the electric potential was expressed as a function of distance from the middle of the electric potential, and then the angle with respect to the axis of the electric dipole. Okay, and then basically if you try to visualize them, it will look like this. Okay, well, we have just learned how to calculate the electric potential difference when the electric field is known, right? And then let's think about an opposite case. How can we calculate the electric field when the electric potential is known? Take a look at the figure on the right, and then suppose this positive test charge is moving between two equipotential surfaces from V to V plus dV. Then the small change in electric potential is dV. And then how do we get dV? Well, just take the equation above and then remove the integral, and then we will get this infinitesimally small change in electric potential, which is in fact minus E vector dot product by ds vector. Okay, and then this is a dot product, so therefore you can replace it with the cosine of the angle between these two vectors. which is shown as theta here. Okay, and then we can rewrite this equation by dividing each side by ds. Okay, and then what you get is that E cosine theta is now equal to minus dv divided by ds. Okay, and then what is E cosine theta? You know, the E is a size of this electric field, and if you multiply by the cosine theta, then what you get is the electric field component parallel to the displacement vector, right? So therefore, we can, if we write this electric field component along S to be E sub S, then if we multiply by the unit vector S, then you get the component of the electric field along that particular direction. And then here, instead of using dvds, we are using a little bit different symbol, which we read as a partial d, and then this differential is called a partial differential. But well, don't be worried too much. This is actually mathematically the same differential that you have learned since high school, but the only thing you have to remember is that in this case we assume nothing is changing along the direction perpendicular to displacement. It is equivalent to saying that we consider all other variables to be constant. Suppose this S is X, and then if V includes Y and Z, then you assume Y and Z are constant, so therefore you are taking a differential only with respect to X. Okay, that's the case. Okay, and then now since you have learned how to get the electric field component along particular direction, now just remember you have to repeat this along X, Y, Z direction, and then once you have done that, you can combine electric field component along three directions using the unit vectors along three directions, and then get the final full electric field component. And then these things, remember, this is the electric field component, which is the partial differential of the electric potential along X, and then along Y, along Z, calculate them independently, and then just combine using this formula. Okay. This is how you calculate the electric field when the electric potential V is known. Okay, and then let's also think about the electric potential of a charged isolated conductor. You know, conductors are important materials for electricity, so it will be very useful to think about their properties. Okay, we actually learned in the previous lecture that if an excess charge is placed on an isolated conductor, these charges will all move to the surface of the conductor and until the charges no longer move. Why? You know, inside conductor, the charges are very free to move. So whenever there is any Coulomb force, they will push each other away, and then the charges will try to move as far away as possible. So that is why they all collect on the surface. And then we also learned that in this situation, the electric field will become zero inside the conductor. It's a very important concept. Okay, so therefore, if you express this electric field in and out of the conductor using graph, it will look like this. So inside the conductor, electric field is zero, and then outside the conductor, of course, it's not zero. It has some value, and then it will start to decrease as you move away from the conductor. Okay, and then how would you get the electric potential in this situation? Well, we already learned how to do it. What you do is that you integrate the electric field following the displacement, and then get a minus value here. Well, I want to talk about is this. Okay, outside the electric conductor, outside the conductor, you can get the electric potential exactly following this integration that we have learned. And then let's think about what happens inside the electrical conductor. You know, inside we still have to do the integration, and then already saw that the electric field is zero. Then if the electric field is zero, then its integration will also become zero. But then this integration is not the potential itself, but the difference in potential. So therefore, the difference in electric potential at the just inside the surface and then deep inside will be zero. The difference being zero means the potential itself will become constant. So there is another very important thing you have to remember, that electric potential becomes constant anywhere on the body of the conductor. It is actually physically equivalent to saying that the electric field will be zero anywhere inside the conductor. Okay, this is something you have to remember. And then there are some additional questions given here. The first question, what would happen if an isolated conductor is placed inside an electric field, which means that you already prepare an electric field and then try to put an isolated conductor inside. Then what will happen? Is the electric field still zero? Okay, we will discuss this in the classroom lecture. And then maybe another question here. Why is it that the birds sitting on a high voltage electric wire don't get electrocuted, right? So we always say it's very dangerous to touch the high voltage electric wire, but then the birds sitting on the wire, why do they don't get electrocuted? Okay, we will also discuss this question in the classroom lecture. Okay, so please think about it at home. Okay, finally, let me make a summary of the lecture. In this lecture, you have learned the concept of the electric potential and its relation to electrostatic potential energy. And you have learned how to draw the equipotential surfaces, and also how to calculate the electric potential when the electric field is known. And finally, how to calculate the electric field when the electric potential is known. Okay, so let's make sure that you remember all of these. And these are the various things we will study in the next online lecture. But we will meet in the classroom on this coming Saturday. I'm sorry, in this coming Thursday. Okay, see you then. Bye.